Hello, my name is Meng Xia. I'm a postdoc from the Hong Kong University of Science and Technology. The paper I will be presenting today is titled QLens, Visual Analytics of Multi-Step Problem-Solving Behaviors for Improving Question Design. First, let's see an example of multi-step question. The question requires students to drag 5 characters to a queue to fulfill 4 conditions. These newly designed questions require students to construct a solution that fulfills a series of conditions by conducting multi-step interactions. To guarantee the high quality of such learning materials, question designers need to inspect how students' problem-solving processes unfold step by step to infer their problem-solving logic, engagement level, and difficulties encountered. And then they can know whether students' behaviors match their design intent and what kinds of guidance should be offered. Some work about game visualization is similar to our work. They visualize the states in the game based on position, and our previous work last year used the transition graph to demonstrate how students pass through each region of interest. Another work used the Sankey diagram to show how students pass through the cases in the programming exercises. This work either cannot reflect students' thinking logic or not scalable to support analytical tasks like comparison. In this work, we present a visual analytics system, QLens, to help question designers inspect, analyze, and compare problem-solving trajectories in order to distill insights for design improvements. We followed a user-centered design process by holding regular meetings with 4 domain experts, including 2 question designers, 1 system developer, and 1 project manager from an education company, to extract their requirements. Here are 4 main requirements. Show students' overall problem-solving performance, summarize and present the multi-step problem-solving behaviors, enable the comparison of students from different groups, and evaluate the feasibility of providing feedback based on existing data. Here is the system overview. It contains 4 modules: data pre-processing, data analysis, visualization, and interaction. In the data pre-processing module, we collected the mouse movement data when students solve the question. It contains the X, Y position and the mouse event on each timestamp. For each question, we first extract the regions of interest by drawing bounding boxes around all graphical components. Then, we number the region of interest as 1, 2, 3, with an order from the top left to the bottom right. For each student, we generate an region of interest sequence by checking whether each mouse position lies inside one of the region of interests. We then recover the intermediate answer sequence. For example, here, the students first drag Mark to the last position. In the data analysis module, we use state transition to model students' problem-solving processes in multi-step questions. Step is the smallest user interface interaction that changes the intermediate answers. Stage is the number of conditions the current answer fulfills. Condition is one criteria that students need to fulfill to get the partial score. In the example, the students first drag Mark to the last position, and he fulfills no condition, so he stays stage 0. And then on step 2, the students drags Paul to the first position, and he fulfills the first condition. Mark stands ahead of Paul, so he moves on to stage 1. In the visualization module, we use a glyph-embedded Sankey diagram to show how a group of students solve the question. The x-axis represents number of steps. A student makes a step when he or she changes the answer. Y-axis represents the number of stages. A student moves to a stage when he or she fulfills a certain number of conditions. We use a glyph to represent students' performance on a state. The number of rectangles represents the number of conditions. The color represents how many students fulfill a condition, and the width represents how many students reach a state. The transition lines between the glyphs show the number of students going from one state to another. We also use a dual axis to show students' average time and trajectory length on each step to indicate their engagement level. The step stage constitutes the first level of the state. The intermediate answer students feel would be shown when hover on the glyph. This data constitutes the second level of the state and would be used when calculating the data-driven recommended path. The transition view introduced above is the main view of our system. In fact, QLens has 2 other views: Overview, which shows the overall distribution of students' performance. Comparison view compares the problem-solving behaviors among 2 or more groups. Now we describe how our system can help question designers check the gap between problem-solving behavior and design intention. Still this question, students are required to drag 5 characters to the queue in order to satisfy 4 conditions. The question designer wants students to solve the question from the last condition. No boy is next to another boy. Based on this, students can solve the problem with the least steps. To verify whether students match the design intention, the question designer inspects the transition view. He finds that all the condition glyphs on stage 1 have a darker shade in the first rectangle. On the stage 2, most glyphs have darker shade on the first 3 rectangles and white in the fourth rectangle. This pattern implies that it is difficult for students to come up with the idea to start from the last condition. Therefore, the design intention, cultivating the reverse thinking ability, is not matched with students' problem-solving behavior here. Let's see another example. In this question, students are required to use all the digits to make 2 3-digit numbers whose product is the largest possible. From the solution provided by the question designer, they explain in detail 4 should be put behind 5 instead of 6, since they expect students may have trouble there. From the transition view, we indeed see a thick line on stage 2. From the glyphs on stage 2, we find that the first and third rectangles are all dark, while others are almost white. This indicates that students know where to put 6 and 5, but cannot fulfill more conditions to put 4 into the correct position, as expected by the question designer. This example shows that the design intention matches with students' problem-solving behaviors. The second case describes how question designers compare the problem-solving behaviors of different groups of students to determine the suitable groups for the current question. This question asks students to arrange all these cards to make one number is twice as big as the other number. For this given question, the designers promote to fix the highest and lowest digits first. They compare students from grade 2 and grade 7. By inspecting the condition glyphs of grade 7, they find the first, fourth, fifth, and seventh rectangles become darker, from the bottom to the top gradually. Particularly at stage 4, as highlighted by the red circle, students got the 4 conditions correct. However, students from grade 2 has no such pattern. From the contextual line chart, we find students from grade 7 took more time to think, while students from grade 2 drag without thinking. Thus, question designers think that this question may be too difficult for lower grade students, since they could not catch up with the design intention. In the third case, we want to evaluate the feasibility of evidence-based feedback. This case describes how question designers check whether existing data is sufficient to provide evidence-based passes. From Common Error panel, they find 4 most common errors. For the first common error, the system can generate the high-quality recommended path, as shown in Figure B. However, for the third error, very few people overcome based on existing data. The displayed recommended path has a lot of ups and downs, which was not good and cannot be used as a direct feedback. Therefore, by using QLens, the question designers conclude that current data is not sufficient to provide data-driven, evidence-based passes for all the errors. We conducted case studies with 4 domain experts during the development, and we also conducted semi-structured interviews with another 3 domain experts, 2 question designers from a different educational company, and 1 senior manager. Each interview lasts about 1.5 hours. We first introduce our system and introduce the 3 cases. Then we ask them to free explore the system and ask questions in terms of system usability and usefulness. Overall, all experts confirmed the usefulness and the intuitiveness of the system. Here are selected feedback. They think the insights from transition view will be very useful for the question designer and the system developer. And it is so clear to view the problem-solving process using the visualization like the transition view. However, they also give some suggestions. For example, as more and more learning activities conducted online, it was also very helpful to compare students from different schools. And they also said that the on-the-fly guidance is what we expected but needs more considerations. Our works can be generalized to other event sequence analysis. For example, the video game behavior analysis for the game design, or online shopping behavior analysis for the product recommendation. In conclusion, we present an interactive visual analytics system on multi-step problem-solving behavior analysis to help educators and question designers evaluate question designs. We introduce a novel glyph-embedded Sankey diagram to represent such behaviors in terms of problem-solving logic, engagement level, and difficulties encountered. We also conducted 3 case studies and interviews with domain experts to provide support for the usefulness and effectiveness of QLens. We also have done many other works on using visual analytics to enhance online learning. Here is the website. Welcome for communication and collaboration. Thank you very much. Any questions are welcomed.